Removing intermediates from rate laws. So last time we talked about how to determine rate laws for multi-step problems. We talked about intermediates, and we talked about how those can't be in rate laws. Now we're going to spend some time saying, okay, but what if we have a multiple step system? And what if when we go to write our rate law and we write it based on the reactance of the rate limiting step? So remember all of that from last time. We write our rate law on the reactance of the rate limiting step. What happens if we do have an intermediate there? How can we get rid of that? And there's a couple of ways that you can do this. We're only going to really cover the one. Too far into it, and it really kind of gets beyond the scope of the class. So let's look at a new reaction. It's kind of similar to our last generic one, just a little bit different. And so here what I'm going to do is I'm going to write out our mechanism, but it's going to look a little bit different than last time. So our first step is going to be our fast reaction. So A plus B goes to C. But notice that it's in equilibrium here. And so remember that equilibrium means that something is going back and forth very, very quickly. If this happens, there's several different things that we can do to kind of cheat the system a little bit and get the intermediates out of the equation. Now our second step is going to be our slow step, and that's C plus D. So our intermediate from our first reaction plus our reactant D goes to E. And then I have one more fast step. So this is going to be a three-step system where E plus another D goes to F. And having three steps is perfectly fine. That's something that's pretty common. Now, I want to do a little bit of a review from last time because we very briefly covered intermediates last time, but let's cover it again. So what are our intermediates here? So remember what an intermediate is. It is made during a reaction and used up during a reaction. So we don't add it in. The reaction makes it and then uses it back up. So in this case, it's both C and E. Because in our first step, we make C, and then we use it back up in our second step. And then in our second step, we make E, and we use it back up in our third step. And so they're both intermediates. And that's fine. You can have multiple intermediates. Now let's look at what we can do if our rate law does have intermediates. Because if we write a rate law just like we did last time here, we run into a problem. So let's look at our slow step. It's the second one. And we have C plus D goes to E. And so here, if we write our rate law, we end up with rate is equal to K2. And you may say, why is that little 2 there? That's just to specify that it's K for the second part. And then our concentration of C and our concentration of D. Each raised to the first power just because there's no coefficients there. But now we have a problem because in the last video, and again in this one, I'm telling you, you don't get to have intermediates in the rate law. And yet here we have C. So we have to do something about that. So here's what we can do given the way that the first step is written. Let's think back to our definition of equilibrium. It means that something is going back and forth, and that the reactants and the products aren't changing. If that's true, that means that they have to be changing at the same rate. Otherwise, the amount of reactants or the amount of products would change. So the forward reaction and the reverse reaction have to be the same rate in order to keep that stable. So we can use that because we can say the rate of the forward reaction is equal to the rate of the reverse reaction. That's the definition of equilibrium. Now what we can do is we can write the rate law for both of those steps. We can say, okay, well, what is the rate of the forward reaction? And we're going to do that exactly the same as we have in the past few videos. We'll say, well, K1 times the reactant A times the reactant B. Now we can do the same thing for the reverse reaction. So we're still in step 1. We're still on the first step of the mechanism. But the reverse reaction now, it flip-flops. So our reactant for the reverse reaction is actually C. And so we say, okay, well, we just put the -1, the inverse there, just to denote that it's the first step, but it's the reverse reaction, times by the concentration of C. And you may say, well, why did we do that? Well, what our goal here is to replace C, to get rid of C from the reaction, or from the rate law. Now what we have is we have an equation that relates C in terms of A and B. So we can rearrange this and we can say, okay, well, let's put everything in terms of concentration C. So I just divided over K1. Once we have this, we can fill it back in to our rate law that we actually want, right? Because our goal is to find that rate law of the slow step. It's just that we can't have C in there. Instead, we need to have C in terms of other reactants. So switching to a new slide, but just kind of keeping all of that information, just rearranged a bit. So this is all the same information. Now we can fill it in. And we can do this. Now, typically, because K's are just constants, we don't necessarily need to keep all of these K1s, K2s, K inverse, or anything like that. We can just combine it all into one big K, and that's fine. That's typically how it's written. Now you might say, well, okay, but this came out to be the same as if I had just written it for the overall reaction. Sometimes that's true. Often even it's true, but not always. And so you always have to go through these steps to make sure of exactly what you would fill in. So while we're doing all this, I need to talk about units, and I decided to just put it kind of at the end of this video so that we get a chance to talk about it here before we start actually calculating numbers for K. So when we look at our K, we need to remember that this is the kinetic K. The kinetic K has units, very unlike the equilibrium K. We're going to use rate laws to figure out these units because it's going to be different for every single order. We're going to look at second order in this video, and then you'll have some homework examples where you go through and you figure out for 0, first, and even a few other orders. So when we look at our rate law, K is going to have to be whatever unit required to match up with our concentrations and our rates. So for second order, I've written a very standard second order rate law. Rate is equal to K times concentration squared. If we look at the units that are on our rate, it's going to be concentration, typically molarity, over seconds, or time. So I'll leave K as is. So if we look at the second row, I've left K just alone. For concentration, I fill in molarity squared. So now moving down to the third row. If we solve for K here, we end up with molarity divided by seconds over molarity squared. We can simplify that by canceling out the molarities to end up with 1 over seconds molarity. And we could do this for any other order as well. So this is to show you second order, but please take the time to go do this for 0 and first order as well. So as a quick review, the intermediates can never be in a rate law. We need to make sure that whatever we do, we get rid of these. If you are given a rate limiting step, which has intermediates as a part of the reactants, you must remove that reactant. We can't just take it away because that was an important part of the rate law. And so what we can do is we can use, if our first step or our step before that was an equilibrium, we can use the definition of equilibrium, that the rate of the forward is equal to the rate of the reverse, to help us out. And of course, go back and rewatch the video if you need some extra help on how to do that. There's going to be other ways to do that, because you might be saying, well, what if we don't have an equilibrium as our first step? What if there's a bunch of other issues? And those do come up, and there are ways to deal with that situation, and there are ways to fix it. It just goes beyond the scope of this particular class, and so we won't be covering it.